Welcome! In this video, we will be discussing trends in atomic and ionic radius on the periodic table. So the periodic table is organized in a lot of different ways, and once we have our elements on the periodic table, we can notice some trends in some of their physical properties. And one of the properties that we can look at is atomic radius. And this is defined as the distance from the center of an atom's nucleus to its outermost electrons in the valence energy level. Right, so if we have our nucleus here and our outer valence shell here, our atomic radius is going to be that distance. It can also be defined as the distance between two nuclei in a molecule that has two of the same atoms. But the big picture here is the atomic radius is going to be from the nucleus out to the valence shell. And if we look across a period on the periodic table, right, so a row, it turns out the atomic radius of atoms that are next to each other decreases as we move across the period from left to right. And this might seem a little bit counterintuitive because our atoms, as we go from left to right, are increasing in the number of protons and electrons. We might think that they get bigger. But that's not true. And to think about this, we have to think about Coulombic charges and interactions, right? So if we have a charge that's positive and a charge that's negative, they will attract each other. But that attraction depends on how big the charges are and how close together they are. So it depends on size and distance. So if we're moving from left to right on the periodic table, the nuclear charge on an atom and the number of electrons increase as we go across the periodic table. And what that means is that as we increase our number of protons, the size of our charge in our nucleus gets bigger. So it's going to have a much greater pull or attraction to the electrons that are in the valence shells. So if we look at the nuclear charge for sodium, and remember the nuclear charge is just the number of protons or the atomic number. So for sodium, we have a nuclear charge of plus 11, and we have one valence electron. For magnesium, we have a charge of plus 12 in the nucleus and two valence electrons. Aluminum has a plus 13 and three valence electrons. Silicon's nucleus has a charge of plus 14 and four valence electrons. Phosphorus is plus 15. 5 valence electrons, and sulfur has a nuclear charge of plus 16 with 6 valence electrons. Chlorine is plus 17 with 7 valence electrons, and argon is plus 18 with 8 valence electrons. So as we go across this row in our periodic table, we increase the nuclear charge. And when we do that, we're going to exert a greater force, a greater Coulombic attraction on these valence electrons. So they're going to sort of suck in towards the nucleus, and it's going to make our radius of our atom look smaller. We can also look at trends going down a group. So if we look at group 1A, as we go from lithium down to cesium, we can see that there is an increase in the size of our atom. So our atomic radius increases. And that happens because with each successive element as we go down, we're going to add a valence shell. And that's going to make our radius bigger. Right, we're adding another shell. It's going to be farther away from the nucleus. So we have a bigger radius. Right, so our outer electrons of successive elements are farther away from the nucleus, so it's going to be bigger. Another thing that happens is that the inner electrons shield the outer electrons from the pull of the positive nucleus. So we have some interference from our inner electrons that make it harder for those valence electrons as they get further and further out to be attracted to the nucleus, so they won't be pulled in quite as tightly. And we can take a look at this right here. So here we've got lithium, sodium, and potassium in their Bohr models. And we can see that for lithium, sodium, and potassium, we're going to have more principal energy levels, more electron shells. So they're going to be much bigger. And then we also have these inner electrons are going to be shielding this outer electron from the nuclear charge. So it's going to probably be a little bit further away than it would be if these electrons weren't here in the middle. And there's a bunch of electrons in potassium that shield its valence electron from the charge of the nucleus. We can also think about ionic radius. So when an atom forms a positive ion, by losing electrons, it's going to have a smaller radius than the atomic radius. So we're losing electrons, our radius is going to get a little bit smaller. The opposite is true for when we form a negative ion. Here we gain one or more electrons, and so the radius becomes larger than the atomic radius does. So if we draw some Bohr models here for our magnesium atom, we have an electron configuration of 282. So we can draw a Bohr model. So here we have our nucleus, n equals 1 with 2 electrons, n equals 2 with 8 electrons, and n equals 3 with 2 electrons. Our magnesium ion has a 2+ charge, which means it lost 2 electrons. And it'll lose its 2 electrons from the valence shell first. So we end up with a new electron configuration of 280. So when we draw our Bohr model again, we'll have 2 electrons in shell 1, and then 8 electrons in shell 2. And now shell 3 is essentially gone, right? It left. So our radius for our ion, in a positively charged ion, is going to be smaller than that of our atom. For the oxygen atom, our electron configuration is 2-6. So we have 2 electrons in shell number 1 and 6 electrons in shell number 2. When we form an ion, we get a 2- ion, which means we're adding 2 electrons to our valence shell. So we're going to have a new electron configuration of 2-8. So there's our nucleus. And we have our 8 electrons in our shell. So we haven't added another shell, but we have added electrons, and they're all negatively charged. So they're going to have some repelling going on with each other, which is going to push them apart and make our radius look a little bit bigger than before. And we can take a look at the trends in ionic radius as we go across the period. And it's going to be a similar idea to that of atomic radius, where as we go across the period, our ionic radius decreases. Again, this is because the outer electrons of the ions are going to be held more tightly by the increasing nuclear charge across the period. So we can see this in this chart as we go from sodium to magnesium to aluminum to silicon. Our atomic radius is getting smaller. We're going to increase our protons all the way through here. Also for our negative ions, remember these ones are bigger than the atom, so they jump up here a little bit. But again, as we go across the periodic table, we get more and more protons, so our electrons are going to be pulled in closer to the nucleus. And we can look at the ionic radius going down a group. And again, this is going to have a similar trend as the atomic radius, And that is going to increase as we're moving down a group. And again, this is because our outer electrons are going to be in higher energy level, principal energy levels. Right, so they're going to be farther from the nucleus due to the presence of additional shells. But again, we have this shielding going on, which is going to, the inner electrons are going to shield the outer electrons from the nuclear charge. So those outer electrons will be able to move a little bit further away. And we can see in this chart as we go across, period, or down, as we go down a group, so here we're looking at the oxygen group, our atomic radius from oxygen to sulfur to selenium to tellurium is going to increase. Okay, so that's it for this lesson. We can take a look at trends on the periodic table. Atomic radius as we go across a row is going to decrease. As we go down a column, it will increase. And the same is true for ions. As we go across a period, ionic radius will decrease, and as we go down a column, ionic radius will increase. Good job today. See you next time.